today we are going to learn all about light.
Wait, there's no video?
Oh, light. Everything you've always, yeah, remind me at the end, we'll do it then. Light is an electromagnetic wave, or at least act like one. Some people think light is a wave. Some people think light is a particle. Some people think light is a particle that acts like a wave. Some people think it's a wave that acts like a particle. Some people answer, if you say, is it a wave or a particle, they just say yes. Because it kind of seems to be both, even though that doesn't seem to be possible, but it seems to be what fits the model the best. So again, there's certain things that are in life and in science that don't seem to be answerable by the model that we have, but so we just kind of make up a double model and say, yeah, we're going with this because that seems to fit the data the best. But light's kind of that way. But if it's electromagnetic, it means three things. Number one, we can travel without a medium, which means we can travel through space. We talked about how with sound, I can scream all I want at you in space, and you won't hear me. But electromagnetic waves did travel through space, so people could talk with radios. And so, yeah, we can travel without a medium. That's cool. In space, all electromagnetic waves travel at 299,782,458 meters per second, which is my favorite number, so you're going to have to memorize it.
I used to memorize, but then I forgot it.
It's easy. If you can memorize a phone number, you can memorize and I know you guys have never had to memorize a phone number, but when I was a kid, I used to have a bunch of them stuck in my head.
So do I. I used to do trouble.
But now we just have phones that memorize everything for us. And then, of course, it means that it's part of the electromagnetic spectrum, which is a mix of all your electromagnetic waves. And you're saying, well, outside of light, what else is in the electromagnetic spectrum, of course? And what else is in the electromagnetic spectrum is all this stuff.
Arrows?
And so you've got that big section there. And of course you can't see. And is that better or worse?
Better, but so hard.
Yeah, better and worse all at the same time because now you can't see yourself. But anyway, you can ignore these little, you don't have to write these numbers down, they're just here kind of for reference. But I do want these words written in that order here. And I want these colors written, and these numbers are important numbers. So make sure you know those numbers. So yes, you write all the names of the colors in order there, and you write the bottom number and top number of visible light. Yeah. So I'll give you a moment to write that stuff down.
Oh, we have to write on the top is long wave and then the stuff in the middle, right?
Right. Long wave, AM, TV, FM, microwave, yeah.
Right, we'll go next. I have to check it to like everyone. What is that? I can't really see what I'm writing.
It's such a joy to teach with numbers.
Write this.
Excuse me. In that big open space area with the arrows, like those arrows.
We should have
Just
just
write this.
Yeah.
No number.
The only numbers you need are the two that I circled down the bottom. are nice and quiet.
Meow. Do you have to write the colors?
Yeah. Okay, so above that first line, the arrow that goes to the right, you should write frequency and energy increases. So as we go to the right, the frequency is getting bigger and the energy is also getting bigger. And below the bottom one, you need to write wavelength increasing going left. So of course, as frequency is smaller, wavelength is bigger. We understand that part. So long wave, these are the huge ones. And these ones, of course, travel over very big distances. And we like that. And then you have your AM radio, and then TV is in the middle of that, and then FM are getting smaller, and then we get to microwave. Now, when you hear micro, it sounds really tiny, right? The microwaves are really about an inch. So compared to radio waves that are measured in meters for FM and hundreds of meters for AM, microwaves are quite tiny. But microwaves were first used in
The
transmission of information. And so we use microwaves because we attach information to the microwave and then send it to another location. And being smaller, it's more directional, and we can kind of point it at something. And so we're developing all these little antennas that point towards something that are shooting microwaves. And one of the first guys that were working on these antennas walked in front of one time when he had a chocolate bar in his shirt pocket. And as he was working in front of this thing and the microwaves were going through him, he noticed that his chocolate bar melted. And then they started doing some experimenting, and they found out that things that have non-polar molecules, like water, are affected by microwaves, and things that have non-polar ones, those are unaffected by the microwaves as far as heating goes. And so that microwave energy can turn into heat energy, and thus the microwave oven was born. And so the microwave oven has been around a little bit longer than you guys have, but not tremendously longer. They came out, they were things that only rich people had when I was in like high school. And they were kind of a luxury item, and now you can pick one up for $30 at Target.
Were they? What was that? 70s?
1242, I think, when I was in middle school.
That's a strange year.
Yes, I'm old. 70s. So now, of course, they're ubiquitous. Everywhere you turn, there's microwaves available, and they're real cheap and much more powerful
That's how
and
technology.
stuff. And some people, of course, are very concerned about microwave radiation, and they think, oh no, you're going to die. Your grandmother especially tells you don't go near the microwave when it's on. It has radiation, don't stare into it or your eyes will melt. There's radiation.
Some people think that putting metal inside the microwave makes explosions, but yet the inside of a microwave is mostly metal.
Yeah, but where the little thing is,
That's causes
it's
sparks.
usually if you have curved metal that you have more of a problem. And so spoons are very bad. Don't put spoons in your microwave. That focuses all the rays. So, I think we've talked about this before, but the word radiation, of course, that freaks people out. But here, all of this is electromagnetic radiation, and so it shouldn't be anything that freaks you out until we get over to the far right column. Then it has a lot more energy, and it's scary. But microwaves are way over here on the left side, so they don't have very much energy. And yes, you can stare inside your microwave and your eyes will not melt, because how big are the holes in the door of your microwave?
Tiny.
They're tiny. And how big did I say microwaves were?
Inch.
An inch. So if the microwaves are bigger than the holes, guess what?
It's gonna bounce back.
They don't go through. So you can stare at your microwave all you want, and it's not going to melt your eyes.
Yes.
You can also put your hand on it to rest for hours and hours.
Yes.
Because you can.
Because I got it. My mom gets it. Show you my stuff.
And some people are very concerned about microwave radiation, like harming us, and we've been using microwaves on an increasing basis in society for the last 50, 60 years, and we found that the incidence of cancer has not changed significantly in that time period. Whereas you guys are around microwave radiation all the time, because 90% of you in your pockets right now have a little microwave radiator called your cell phone. Guess how this talks to the tower?
Lasers.
In microwaves. So you're carrying around the little microwave with you all the time.
So if we got enough together, it'll be cooking.
Okay. Except my microwave at home, my microwave oven at home is about 1400 watts, and my phone is about 1. So I'm not likely to cook myself too much with my phone. Might get a little bit warm, but it's not going to fry me. So I'm in good shape there. We talked in more detail about infrared radiation in the thermal energy unit, right? And infrared radiation, of course, once it hits you, it turns into heat.
Yes.
Anybody remember this?
Yes.
Okay, just checking. Infrared is right next to red, and ultraviolet is right next to. Hey, what do you know? So in between red and violet, we have all this visible light range. So the visible light range is smack dab in the middle of the electromagnetic spectrum. So that's cool. And this is what we see with, is we can see from 700 nanometers up to 400 nanometers. I say up to because I'm talking about frequency. The wavelength is getting smaller, but the frequency is getting bigger. So violet has a higher frequency and a smaller wavelength. Red has a lower frequency and a bigger wavelength. But the biggest wavelength we can see is 700 nanometers. Anything bigger than that, it's invisible to us. Anything smaller than 400 is invisible to us. Now, there are some bugs that see real well in the ultraviolet range and things like that. In fact, if you look at flowers in ultraviolet light, they have a completely different pattern, and they look different because a lot of bugs see in infrared. And so when they're flying down, these flowers show up to them totally different than they show up to us. So that's kind of cool. But yeah, the range of visible light is between 700 and 400 nanometers. So as we go to orange, yellow, green, cyan, blue, violet, they're getting smaller and smaller and smaller wavelength, higher and higher frequency. And so those are the colors in the order that they go in. Some of you may be confused about the cyan. Some of you may have memorized the colors of the rainbow before, and they were different. Yeah, Roy G. Biv. What happened to the Biv, man? Now it's Roy G. I changed this. I don't know if the rest of the world has changed with me because I do things that make sense. But 200 years ago, when Roy G. Biv was a popular acronym, we called the sky blue, and we called blue jeans indigo. How many of you call them indigo jeans? Okay, you don't. We don't use that color anymore. We now call that color blue, and we call the light blue that's the sky cyan. And cyan is a very definite color in today's world because we deal with these in many different industries. So now basically these words make more sense, but it doesn't make Roy G. Biv anymore, so some people get very sad. And violet, of course, is right next to ultraviolet. So yeah, you need to know the colors of the rainbow, and you need to know the frequency range there of what's visible. So once we get invisible, we go to ultraviolet, and ultraviolet, they break up into a couple different categories, and you have UVAs and UVBs, and the A's are closer to us, and the B's are are farther away from the visible light, and so A's and B's, they're different and more dangerous. What are ultraviolet rays dangerous on? They have high enough energy that they can actually cause some genetic mutations in what they hit. And what do they hit on you? Your skin. And so that can cause this lovely thing called skin cancer, which comes in 3 various forms, and my wife has had 2 out of the 3. Not good. So, yeah, those of you who live in Laredo, hey, that's all of us, probably noticed that, yeah, sometimes if you look on the Weather Channel, they have things that we'll talk about the UV exposure index, and 90% of our months here are 10 plus. It's supposed to be on a scale of 1 to 10, but we're regularly over what the 10 is for the rest of the world. So, this is a wonderful place to get skin cancer. So, I don't think you need to stay inside and become mole man, but they do have this stuff called sunblock that is possible to put on your epidermis and hopefully avoid that skin cancer stuff. And get to know what skin cancer looks like so you can spot it early. Because half of you will probably get it at some point in your life. Nope. We have more than they do.
Well, this is interesting.
Yes. We're close to the equator and we have more sun. Okay, going past ultraviolet rays. Oh, by the way, what soaks up ultraviolet rays? We have a layer in the atmosphere called the ozone layer.
Yes.
And the ozone layer, when the ultraviolet A hits, it breaks it into double, and then when that gets broken up by the UVBs, and so the A's and the B's both get broken, they break apart ozone, and then the ozone reforms again. And we like that because it provides a shelter. So most of that energy gets used busting up the ozone on the way here to Earth. And so having a nice thick ozone layer is helpful to us because we don't get that increased radiation. If we didn't have an ozone layer, we would all be dead. Yay! One more. There's a bunch of little protective layers that we have around the Earth that provide the opportunity for life, which is really nice because I like to be alive. But if we didn't have these, then we'd be in trouble. So the ozone is very helpful to help block out ultraviolet. If we go past ultraviolet, we hit X-rays. And what are X-rays good for? Yeah, we can see inside your body. And we talk about how ultrasound is a good way to see inside your body. It's better than X-rays because it doesn't harm you. X-rays, again, if ultraviolet can cause skin cancer, X-rays can cause cancer much deeper because it's even smaller, so it's more penetrable, but it's also higher energy. And so X-rays can go into your body and they can cause mutations. Now, the benefit versus the risk is, hey, I think I broke my arm. There's a benefit to checking to see, did you break your arm or not? And so you can look at your bone that's more dense with X-rays that you can't with an ultrasound. And so there's advantages to using X-rays, but you don't want to go and get X-rays twice a day, every day. That's bad. So that's where your risk starts outweighing your benefit. If we go past X-rays, we get to? And what are gamma rays good for? Apparently gamma rays are good for turning you into the Incredible Hulk. Because Bruce Banner was covered in gamma radiation from a nuclear explosion, and that got him turned into the Hulk. And of course, cosmic rays are good for turning you into the Fantastic Four. So,
Awesome.
yes. Cosmic rays. Now, if we get to cosmic rays, the frequency is so high that the wavelength is so tiny that by the time you're down to gamma rays and cosmic rays, you're actually smaller than atoms. These rays are. In fact, cosmic rays are so small that they can go right through an atom and not hit anything because atoms are mostly empty space. And so if you're that small, you go right through the atom and it's not a problem at all unless you hit the nucleus.
Oh no.
Now, if you actually hit the nucleus, which is a 1 in a billion shot, but there's lots of them to go through, so yeah, you can have cosmic rays go right through your body and not actually hit anything. They're that small, so they can go through that empty space. But if they do hit something, and they hit that nucleus, what they can do is they have so much energy they can actually turn a neutron into a proton. Or is it a proton into a neutron?
No, it's
Yeah, the neutron into a proton. So if it turns a neutron into a proton, of course, it changes what the element is. This happens a lot in the atmosphere, especially in the upper atmosphere, where these hit, and it's only in the upper atmosphere because our magnetic shield goes around and kind of deflects a lot of this stuff, which again is really good for our being alive. But in the upper atmosphere, we have a lot of what's the main thing in the atmosphere? The main element? Anybody? Nitrogen.
nitrogen.
And nitrogen,
Awesome.
if we knock out a neutron and turn it into a proton, would turn into. It's the other way around. We knock out a proton, turn it into a neutron. So if we knock out a proton and turn it into a neutron, it's going to turn into carbon. But it's still going to be as heavy as nitrogen was, so it's still going to be 14 like nitrogen is. So now all of a sudden, instead of having carbon 12, you have carbon 14. Has anybody ever heard of carbon 14 before?
Nope.
That's the radioactive carbon.
Is that not good?
So because it wants to lose something and turn back into nitrogen. So we have that radioactive carbon, and that happens because of cosmic rays smacking into it largely. And of course, there's a difference. If you learned anything in chemistry class, hopefully you learned, if you got to the organic section, that carbon was good at it could make 4 bonds, and nitrogen could only make 3 bonds because it already had some paired electrons over on the other side. You guys remember learning this?
Yes.
Okay, so if I turn nitrogen into carbon, hey, that was groovy. But if carbon pops back into nitrogen, then what happens? Well, if he was holding hands with 4 people, he has to let go of somebody. Most of the mutations that we have in our bodies come from the loss of information. This is how you lose information. When carbon is holding on to something, if it was just holding on to a hydrogen, no big deal, it just lost that, and it gets replaced next time the DNA replicates. But if the DNA gets damaged in this way, a lot of times it can drop some information along one of those pathways, and so we end up losing information. So it's kind of interesting there. You get to be a mutant.
You're the X-Men.
Yes, so we're the X-Men caused by cosmic rays too, I guess. Anyway, the first person to accurately clock the speed of light was?
Oh, what's his name?
This guy.
Trey.
Anybody recognize him?
Mr.
This me?
His name was Albert Einstein. No, Einstein wasn't the only Albert. Look at his hair. His hair was nice. Einstein had hair like mine. It was all over the place. This guy actually had hair. I don't know if it was his hair, but it was somebody's hair. And it looked nice. This is Albert Mitchelson. Mitchelson. Albert Mitchelson was clocking the speed of light between 2 California mountains in 1926. And he ended up clocking that speed of light quite accurately, proving that light did in fact have a finite speed. Actually, there was a time period where people thought that light was infinitely fast. And a Danish scientist named Ole Romer was the first one to prove that light did in fact have a finite speed, but he couldn't figure out what that finite speed was. He just knew that it wasn't infinite, and he could prove that. But what Mitchelson did was he clocked the speed of light as this number and got a pretty nice number out of it. And for that experiment, he won a Nobel Prize making him the first American scientist to win a Nobel Prize. So, yeah, Albert, we love him. But here's the interesting part. He wasn't actually trying to do this. This was the byproduct of his experiment. His actual experiment was he was trying to prove that there was actually a medium in space that they called ether back then, which is confusing because it sounds like the chemical ether, which is very different. But anyway, he thought that there was a medium in space that allowed the wave to travel through space. And so his experiment was trying to prove some characteristics about this ether that they had made up. And this experiment was a dismal failure. It proved that ether did not exist, but he really wanted ether to exist. So when his experiment proved that it didn't exist, guess what he did? He was like normal people. There must be something wrong with my experiment. And scientists are like this too. There's a great comic strip called Peanuts. Have you guys ever read that? Okay, so there's one time where Linus and Lucy are walking down the sidewalk, and Lucy says, "Hey, there's a butterfly on the sidewalk." And she goes, "That's weird. You don't see butterflies very much this time of year." She goes, "Well, maybe it came up from Brazil. Sometimes they do that. They fly all the way up from Brazil." And then Linus looks closely and it says, "That's not a butterfly. It's a potato chip." And she goes, "That's weird. I wonder how a potato chip got all the way here from Brazil." And I think that's the way we are sometimes as people. We get so convinced that something is right that don't let the facts get in the way. So that can happen sometimes. And so Mitchelson, he was very committed to his idea of this ether, and the facts didn't get in the way of him trying to prove that his experiment was wrong. So he spent a lot of years trying to prove that his experiment was wrong so that ether would be right, and it never worked out well for him. But he did win a Nobel Prize for this part. So, yeah.
How do you figure out the speed, by the way?
What he did was he had two mountains that were a certain distance apart in California, and on top of one he put a mirror that spun around, and over here he had a very bright light that he was flashing that direction, and he was over here watching. So the light had to travel here, hit the mirror as it was spinning, and come back. And so you would get little pulses of light because of the spinning of the mirror. And so by timing it and knowing the distance and everything, he was able to figure out what the speed of light was. So it was kind of a cool experiment. But you had to have a real big distance for this to work because light goes really fast. So anyway, there are three ways of describing light transmission, how light travels through things. And we have things called transparent, we have translucent, and we have opaque. Transparent means the light moves through with little or no distortion. And so these are things that are transparent. Clean air, water, glass, soda, plastic, these are all things that are transparent. The light moves through them. You can see what's inside of them with almost no distortion at all. Then we have translucent. Translucent, the light does go through it, but it gets distorted. So you have white milk jugs. You can see how much milk is in there, but you can't really see the milk. You have your skin. You can see blood veins and things underneath your skin, but you can't see them directly. You have shower glass. You can see that there's a body inside, but you can't see the exciting parts. So that's example of translucent. Opaque, on the other hand, light does not pass through. So you have things like brick wall and wood and bone and metal. Those are examples of opaque. But have you ever held a piece of paper up to the light? Yeah, like I can see this where it says shower, this where it says glass, that where it says butt. And so I can see this on this side because the light is going through. But the paper, I don't really see well through it, so I'm tempted to call it opaque, but clearly light is going through or I wouldn't be able to read it, right? Yeah. So is it opaque or is it translucent? Sometimes it's hard to tell. And that's because there's not something that is just like, boom, this is transparent, and then boom, this is translucent, and boom, this is opaque. It's a continuum. So if it's a continuum, there's not a definite line between one and the other. So sometimes it's going to be a little bit more difficult. Is that transparent? Is that translucent? It's kind of open to interpretation. Now, the wrapper here, the clear part is pretty transparent, but yet you get kind of blurry, right? And definitely by the time you get some color in there, it's more translucent for sure. And then that's starting to borderline opaque. So it's like that. Sometimes it's a little bit hard to tell, but there are some definite things that fit within each category like we have there. Moving on, when light bounces, we call that a reflection. Very good. Yes, bouncing is always a reflection, and we're going to learn about reflecting light. It's really easy. If I bounce off a smooth surface, we call that a regular reflection. And if I bounce off a rough surface, we call that a diffuse reflection. If it's a smooth reflection, you can see yourself. And it's a diffuse reflection, you can't see yourself. So how do we know if it's smooth or rough? Well, if the bumps are smaller than one wavelength, then it's smooth. And if the bumps are bigger than that, then it's rough. So if it's smooth, what happens is all the light rays that come in together bounce out together. So they're all going to bounce like that. So if I have 3 coming in parallel, I'm going to have 3 going out parallel. But if my surface is kind of bumpy lumpy, then if I have 3 that come in parallel, they're all going to hit a different angle. And so they're going to bounce off. Instead of coming in together, they're going to bounce off in different ways. They're going to scatter around. That's why you can't see yourself in that. You can see how you can see yourself in the first one because everything that comes in goes out, so it's all going to look the same. On this one, the light's just going to go, and you're like, "What? I don't see that." So if you've ever stared at yourself in a piece of wood and wondered why you get such a bad reflection, it's because wood has bumps that are bigger than one wavelength. But if you look at nice smooth glass or smooth calm water, that sort of thing, then you can see yourself in it. That's much smoother, so that's smaller than one wavelength.
So if you could smooth down wood enough, you might be able to see yourself?
If you could smooth wood down that much, you would be able to see yourself, but we can't smooth down wood that much. But you can apply coats of stuff that make it that smooth, and then you can see yourself. So if it's like lacquered wood, then that can get down that smooth. But that's when we're talking about visible light. What if we're talking about microwaves? How big did we say those were? An inch. So as long as the bumps are smaller than an inch, then microwaves will bounce off it quite nicely. So if you look at the wall, we've got all these little tiny bumps in the wall here, and then we've got the joints there in the wall, and the joints are smaller than an inch. So if I'm bouncing microwaves off this, does it even notice that this is bumpy? It's going to come bouncing off it just like light bounces off here. This is nice and smooth. I can see you guys in the reflection of that board. But the wall, the microwaves would bounce off it just as well.
So we can microwave each other.
If we have, yes, we can microwave. If we have even bigger waves like radio waves and TV waves and things, then we don't really have to be that smooth at all to get a good bounce off of those. And so it kind of works nicely that way. If you probably aren't old enough to remember the old satellite dishes that people used to buy that were like 10 feet across. And they had these huge satellite dishes that took up their whole backyard. And
Some people still have satellite.
yeah, and those, well, the new satellite dishes are only like this big, so they're much less obtrusive. But the big ones that they had, they were oftentimes a big screen on the back. And you're like, well, doesn't all the waves just go right through all the holes there? No, as long as the holes were smaller than the wave that was coming into it, the wave thought it was solid and bounced right off of it just nice. So that's how we get regular and diffuse reflection. If the reflection formula is quite simple, stop it. This should be the last thing you write down in the front, right? So in that box, you're going to write angle in equals angle out. That's tough, right? And you're like, wow, that's so difficult. How do you make that work? If you've ever bounced a ball, you know the angle of reflection. If I bounce it straight down, it bounces straight up. And if I bounce it at an angle, it comes out at an angle. And so you've seen this if you've ever bounced a ball. Now, how do we measure these? We measure them from the normal. So, of course, you're wondering how I would measure that because I'm kind of abnormal. But angles are measured from the normal, and a normal is a line that's perpendicular to the surface, and we measure all of our angles from that. So we're going to find out that there's a name for the incoming angle, the outgoing bounce angle, and anything that's going into the new material. So you have this beautiful diagram already on your paper, right? Yeah, what a pretty diagram. And by labeling the diagram, we're going to answer these questions. So the angle that comes in, we call the angle of incidence. So the incoming angle is the angle of incidence. And that's really easy because it starts with in, when it's coming in. So the bounce angle, people always think should be called outcidence, but it's not. So what is it doing up at the top? It's reflecting. So this would be the angle of reflection. And so we have the angle of reflection is bouncing off. And at a medium boundary, some of the energy is going to reflect, and some of it is going to go into the new material. But the stuff that's coming into the new material, it's not going at a straight angle in. It gets bent in toward the normal in this situation. And so again, this would be the normal. This is the one that's perpendicular to the surface. So this is being bent in toward this normal that's there. And so as it gets bent into there, what is it doing as we're entering a new material? When we enter a new material and we bend, it's called refraction. So that's going to be called the angle of refraction. So you both get to label this and answer these three questions all at the same time. Everybody catch that trick? So again, in any medium boundary, some of that light gets reflected, some of that light gets refracted. All unless we're coming out of the more dense medium into the less dense medium past the critical angle, which we'll talk about in a minute. How much do we refract? Well, to find out how much we refract, we have to use Snell's rule. And Snell's rule, you get to write in that next box. The little blank above it that has an apostrophe S, you write Snell. So Snell's rule is called the law of refraction. And Snell's rule, of course, is n1 sine theta 1 equals n2 sine theta 2. Isn't that pretty? Mr. Snell was genius if he came up with that one. Angle 1 and angle 2, this is going to be the angle of incidence, and this is going to be the angle of refraction. Well, just 1 and 2. The n numbers are called the index of refraction, and the index of refraction basically tells me how much bend do I expect to get, or how much did I slow down because I'm going into the new material. So the index of refraction is a number that tells me how much a material will bend that light, how much it will slow down. So the bigger the n is, the slower light is traveling in that. And so there's a formula for that, and that says n equals c over v, where c, of course, is 299,792,458, and v is the velocity of light in that substance. So the bigger the change, the bigger that n number is going to be. So the n of air, well, the n of a vacuum is 1.00. Air is pretty much 1.002 because you have to go decimals past that before they start showing up. So air is going to be 1, but like glass is 1.5, water is like 1.3, diamond is like 2.42. It's much slower in diamond than it is in glass and water, and so it bends more. So we talked about before with refraction how you're entering that new medium, and because you're traveling at different speeds, you're going to bend. You guys remember that? Okay, so that's why the bending happens, and so we measure this. So Snell figured out that there was a sine relationship there, which, yeah, way too much time on his hand. Not enough disc golf, right? Yes, ma'am. So, a light ray hits a diamond at a 68-degree angle. What's the measurement between the incident and reflected angle? And at what angle is the light refracted into the diamond? So we know that this angle coming in is 68. What should the angle going out be? That should also be 68. So the angle in between these two should be?
136.
136. Very good. So if it's 68 in, it's 68 out. So the total in between them has to be the total. So if I go 68 here to the normal and then 68 more, the total in between those two is 136. Now, if we're going to do the second question, we have to know what is the index of refraction up here in air and down here in the diamond. So in the air, it's going to be 1, and in the diamond, it's going to be 2.42. So we're going to stick these into Snell's formula, and here's the only trick. There's not much of a trick to it. You say, in the air, what was the angle in the air? Well, in the air, it was 68. So the 68 goes with the index of refraction of air, and I don't know what the angle is in the diamond, so my unknown goes with the angle in the diamond. Get it? So n1 sine theta 1 equals n2 sine theta 2. We're looking for x. So if I'm looking for x, first I got to find the sine of x, so the 2.42 needs to algebra underneath. And then once I get that answer, I need to unsign it. So I have to hit inverse sine, or sine to the minus 1 of that answer. And if I do that, I get a number. Your calculator should be in what mode? Degrees. Again, if you're in radians, it will lie to you when you hit sine, cosine, and tangent. Did anybody find an answer? No way. That's what I got. I got 2.52793.455. Which, of course, I'm just going to round to the nearest whole degree. So 23 degrees. So notice it got much smaller once it was in the diamond. Because it slowed down a lot. That math isn't too hard. Next, we're going to differentiate between luminous and illuminated. Luminous means I give off my own light. What inside this room is luminous?
Bulb.
Not right now, the bulbs are.
That's not the computer.
Yes, the computer is giving off light. The projector is giving off light. Is this screen giving off light?
Why, yes, there's a tiny light on the side.
Yes, it seems like it's giving off light, but it's actually just reflecting the light from the projector.
Not
But
that
yes, but it's got a little LED over here on the side. That's luminous. And so there's a bunch of different LEDs. Your calculator might be luminous depending on which calculator. If you turn on your phone, it becomes luminous, and if you turn it back off, then it's not. So, of course, your phone should be off.
The Christmas tree.
My Christmas tree is luminous. How pretty. Still no chocolate underneath it, though. I'm just saying. Luminous objects give off their own light. Illuminated objects reflect the light from a luminous one. So, you guys, I can see not because you are glowing, but because light is coming in from the window. What is providing that luminosity?
The sun.
The sun. So the sun is very luminous. It gives off a lot of its. Yes, the Illuminati are illuminated ones. Anyway, Anyway, our classic example is the moon is illuminated by the luminous sun. Have you ever looked at the sun and saw it only look like a smiley face, like you see the moon sometimes?
Yes.
No,
It smiles at you.
see the sun look like a smiley face here in the middle of an eclipse. That doesn't normally happen. But the sun or the moon can change shapes because it's only reflecting light. It's not giving off its own light. And so it reflects it based on our relationship between where we are and the moon is and the sun is. So the moon gets shadows like that. Polarized light is light that's all waving in the same direction. So it's all cresting up and down, or all cresting side to side, that sort of thing. Light, all electromagnetic waves are transverse waves, not longitudinal waves, so we have crests and troughs. And polarized light, we can discover stresses in transparent objects. We use them to make 3D movies, and we use them to tell whether a mixture of chemicals is man-made or organic. Organic molecules, ones that are made by living things, are all the same shape. They will all twist to the right or all twist to the left, and so they call them right-handed molecules or left-handed molecules. But if we make these in the lab, we get an equal mix of right and left molecules. And so if we shine polarized light through it, you will see it actually twisting one way if it's organic, and won't twist if it's man-made. I will show you how it detects stresses here. And I have to get close to you, which scares me. You guys are so far away. Okay, so here I have a couple polarizing lenses. And if I bring the polarizing lens back here I have a little piece of transparent plexiglass, and if I squeeze it, you can't tell that it's under stress. Just by looking at it, it looks no different if it's not under stress or if it's under stress. But if I stick it here in the polarizer and I stress it, unstressed, unstressed, stressed. Chris. Just leave it around and walk around so you can see it. I expect you to see if this is unstressed, that's stress. See how you can see it? Unstressed, stress.
Why is it?
So, if I hold this in front of my face, can you see if I'm stressed? No. And so I have sunglasses that when I wear my sunglasses, they're polarized sunglasses. And so the polarized sunglasses are really nice because the glare that bounces off of your car's windshield and off the road all comes up polarized. And so that cuts it off. And so that's really nice because that reflection gives you a headache and you don't like that. But since it is polarized, then I see everything has a stress in it when I'm wearing this. If you look at windows in your car, the tempered windows, they all have these little stress marks all over the place, and you can see them in that. I look at my camera and there's a little thing on the top of it that's stressed out. And another thing that was really cool that I found out is your phone screen is polarized. So, like here I have two polarizers. And what you can do is you can think of a polarizer as being prison bars. If we have prison bars that are going up and down, and I'm trying to make crests and troughs go up and down, they're going to go through it, no problem, right? But if I try and make crests and troughs go side to side, they're going to hit the bars and not go through. That's the same kind of thing these are. So these are both waving the same direction. But if I take one and I turn it 90 degrees, now what happens? So here they're the same, here they're different, they're opposite, so it's cutting everything off. So I can dial in how much I want to see you or if I don't want to see you more. So that part's kind of cool. But what gets even cooler is if I take a third one that's at 45 degrees and I put it here, nothing. But if I put it in between, magic. How cool is that? Okay, so if I'm staring at something that is polarized, it's real cool. If I look at your table this way, I see the shine on the table. Do you see how it looks kind of whitish when you look at the table at an angle? Yeah. Here I see that shininess, and here the table just looks black. So it's polarized reflection, and here it's not. See the white? Dark. Hey. So polarizers are used in photography because you see the glare off of a window, and if you do the polarizer at the right angle, then the glare goes away and you can see through the window. So that's that.
So those photography cameras have two lenses.
No, you can put a filter on the front. That's a polarizing filter.
You just turn it whenever you need.
Correct. So you have to turn it like that, and you can make your sky bluer and things like that. Movies. Have you ever been to a 3D movie?
Yes.
The glasses you're looking through are these. And what happens is we film this like this, where one of them is being filmed this way and one of them is being filmed this way, and they're at angles. And so we have two different cameras that are filming this, and of course, just like your eyes, when my eyes are looking at something close, they're crossed, and when they're not, they're more parallel. And so the cameras are doing this, and you're actually projecting both images. If you've ever looked without your glasses, it looks all blurry because there's actually two images up there at once. And what happens is this kills the wrong image, and then that one kills the other wrong image. So you have two different ones, and you're making sure the right image is going in the correct eye. And so we're using these to cancel out the other one. That make sense? That gives you the right information in the correct eye. If you turn sideways, it's not so good. Now, what I learned is your telephone, the LCD screen on your phone is also polarized. I found this out with my iPad one time. I was in the car, and I had my polarizing sunglasses on, and my wife went into a store for a minute, so I grabbed my iPad to check something, and I hit the power button, and it didn't turn on. And it's like, I know it has battery, what's the deal? And I thought, man, this thing is broken, I don't know what's wrong. And then I turned it, and then I could see. So what happens was I was at the wrong orientation, which I should be able to show you here. So, of course it doesn't work on this screen. Yeah, it gets a little darker, but on my iPad it's like completely dead one way and then alive the other way.
You should bring that in so we can see it.
So I didn't bring my iPad today, so it does change colors on this one. Okay, if it changes colors on this one, that means we've got two different ones. We've got the same thing on the Iki here. What color do you, here, I'll turn off the light so you can see this better. This has two different screens inside of it, and they're at right angles to each other. So here I'm killing one of them, and here I'm killing the other one. So see, now I'm more purple, and now I'm more green. Does anybody go to Gutierrez? Yes. Purple, green, purple, green. You guys weren't gators? No. Okay, just checking. My oldest kids were gators. Okay, so that's polarized light, at least briefly. And again, we're going to polarize light with either filters or by bouncing it. Last thing is lasers. Lasers are light that is coherent, which means not only are all the crests cresting in the same direction, but they're all cresting at the exact same time. So lasers, the coherent light, is more than just polarized. Lasers are polarized, but they're that. And laser, of course, is an acronym that stands for light amplification by the stimulated emission of radiation. Isn't that cool? Total internal reflection occurs when light is trying to refract out of a more dense medium past the critical angle. The critical angle is the one that refracts out at 90 degrees over the boundary line. We are going to run out of time, aren't we here? Okay, I'll give you some examples of this tomorrow. Fiber optic. Anybody ever looked into an aquarium and noticed that you can look straight through it, no problem, but if you look in and then out the side, you see a mirror?
Yes.
That's because when you're looking out that side, you're looking past the critical angle, so you're getting total internal reflection. So you end up looking and seeing mirrors. Here you can't tell, am I looking through this or am I looking at reflections? Is my daughter underwater? Is she next to me? Is she on the other side? But if you look at the top, this is the top level of the water here. That looks like a mirror up on top. So when I'm inside looking up, I'm hitting past the critical angle. I'm hitting total internal reflection. Again, we'll show you how that works tomorrow. And apparently we'll watch our study tomorrow also.